Today I will talk about HuggingFace and how it integrates with Ray AI Runtime. So before we start, just a quick show of hands, please write in the chat. Just wanted to know how many of you have heard of Ray, how many of you have worked with Ray and with HuggingFace or transformers in particular, and how many of you are data science or machine learning practitioners. So just please write while I continue. So a little bit about myself. So my name is Antoni. I'm a software engineer at Anyscale. I've been with Anyscale for almost 2 years now. I'm working on the libraries team, which means that I handle the Ray AI runtime and libraries such as RayTrain and RayTune. And aside from that, I'm also an open source enthusiast, and I contribute to and maintain several machine learning related open source projects. So a little bit about Anyscale. Anyscale is the company behind Ray, an open source unified framework for scalable computing. And our mission is to make scalable compute for AI and Python as easy and as robust as possible. And we do it because scaling is a necessity and scaling is difficult. And we want to make it as accessible and as easy to use as possible. So what are we going to talk about today? First, I'm going to quickly introduce HuggingFace and how it can help you with using cutting-edge machine learning. Then showcase why distributed training is a must in today's machine learning environment, and how you can make that distributed training easy by combining HuggingFace and Ray AI Runtime or Ray AIR. Then we'll deep dive into the internals of the Ray AIR's HuggingFace trainer, and finally we'll conclude with a live demo showcasing a typical workflow you might do with the HuggingFace integration in Ray AIR. So just quickly to recap, provide some context about the current state of ML. So as I hope we all know, deep learning is state of the art, especially for unstructured data, such as text, vision. There is also some progress in time series forecasting and so on. And all of this has led to some quite impressive foundational models, so such as GPT-3. I'm not sure how many of you had a chance to, for example, play with the new ChatGPT by OpenAI. It's really impressive. And all of this, this growth and this increase in complexity of foundational models has led to some very exciting use cases, especially in the natural language processing and natural language understanding category. So, for example, we have tasks such as text classification, sentiment analysis, entity recognition, for example, names in legal documents, automatic translation, detection of toxicity in social media, sentence completion, text-to-image generation, Q&A, and so on. And this also has led to a necessity to fine-tune those foundational models so that they may be better on the specific task that we want them to perform. And aside from that, the models themselves are not only growing bigger in size and complexity, in the amount of parameters that they have and the amount of compute that they require, but the data itself is also growing bigger and bigger, still necessitating more compute and more memory. And we are also approaching a point where machine learning is pervasive across all domains and businesses. And there are plenty of use cases for machine learning that can improve the business. So just to quickly introduce what is HuggingFace. So HuggingFace is a simple, robust, and powerful library for Python, which provides an opinionated and high-level API, which wraps around various state-of-the-art machine learning models such as GPT, BERT, and so on. It's mostly focused on NLP, but there is also some additional focus on audio classification, image generation, and so on. And most importantly, it has a huge community and social focus, especially thanks to its HuggingFace Hub, where users can share and obtain pre-trained models, data sets, and immediately apply them to their use cases using the simple and accessible Hugging Face APIs. So how does Hugging Face make machine learning easier? So first of all, it abstracts away many complexities of machine learning and deep learning. You don't really need to reason about the underlying neural network architecture. You do not need to be an expert in PyTorch or TensorFlow to take advantage of all the state-of-the-art models that Hugging Face allows you to use. And because it provides a high level of abstraction and simple to pick up APIs, it also leads to great developer velocity, meaning you can basically apply whatever you may require to your use case right away. And finally, as I mentioned, there is the Hugging Face Hub, from which you can obtain different models and datasets. So a typical Hugging Face workflow would be that you obtain a pre-trained model, then you fine-tune it to your use case, and then you can use Hugging Face pipelines for inference at scale. So let's quickly see a simple code example that illustrates this. So first of all, we use the Hugging Face datasets library to load a dataset from a Hugging Face hub. Then we split it into a train and test datasets. Then we obtain the model from Hugging Face Hub as well, which is the BERT model. And it's already pre-trained, and we may fine-tune it if we want, or we can just use it as is. Then we specify the training arguments because we want to fine-tune it here. Then we initialize the Hugging Face trainer object, passing the model, the training arguments, and the dataset. And finally, all we need to do is to call train, and Hugging Face takes care of everything internally. So of course, those state-of-the-art models, they allow us to do things that were not really thought of in the past years, but the downside is that all those models need a lot of compute. So the problem is that it is simply not really possible to train or even perform inference at scale on single machines. So the amount of compute required with each new foundational model, with each new research breakthrough, has been simply outpacing the growth in hardware performance on a single node. So of course, the Moore's law for CPU is simply unable to catch up. And even if we consider hardware accelerators such as GPUs, if we were to train GPT-3 on a single Tesla GPU, it would take hundreds of years. In other words, since we cannot really train the models and perform inference at scale on single nodes, on single machines, what we have to do is we have to go distributed. We need to scale out horizontally. But that, of course, brings new problems. So first of all, our developer velocity is going to go down a lot because we need to learn new APIs. We need to learn new libraries that make distributed computing possible. We need to consider new problems such as how to communicate between nodes, how to do checkpointing effectively, how to transfer data between nodes. Furthermore, we need to learn how to manage complex infrastructure. When we use a cloud provider such as AWS, GCP, and Azure, now we need to learn new APIs. We need to learn how to create new nodes, how to create new clusters. And this is all knowledge that is not necessarily required for our core task, which is to take advantage of a fine-tuned foundational model or any other model in that case. And finally, even though we may succeed in scaling up the training or hyperparameter tuning or inference itself, we need to keep the entire end-to-end machine learning pipeline scalable because it's going to be as slow as the weakest link. And if we are unable to scale up the entire experience effectively, then we are not going to reap the benefits from scaling in the first place. So the solution that we have created to those problems is Ray AI Runtime, or Ray AIR in short, which is a scalable unified toolkit for both data scientists and software engineers. And it provides a flexible and Pythonic framework for each step of the machine learning workflow. So Ray AIR is the glue that holds together different Ray libraries. And for example, for data ingestion and data processing, you can use Ray Data. For training, we provide Ray Train. For tuning, we provide Ray Tune. And for inference and serving, we provide Ray Serve and Ray Data again. And Ray AIR is a set of unified APIs that make it easy to transition between those libraries. So if we take a look at the Ray AIR ecosystem, we can see that it is built on top of Ray for open and flexible support for ML compute from end to end. Ray Core provides the primitives on top of which Ray AI Runtime implements different libraries. And it leverages integrations, storage, tracking. And Ray AIR has high-level libraries that make it easy for both data scientists and machine learning engineers to conduct distributed computing in their AI and ML use cases. Furthermore, Ray AIR contains multiple integrations for all of the popular libraries for different steps of the machine learning pipeline, allowing you to keep using your favorite tools without having to relearn new APIs or new frameworks. So why use Ray in the first place? So first of all, Ray provides an efficient data layer and distributed object store, making data sharing between the nodes in a cluster easy and seamless. Ray provides a Python-based API, allowing you to write all of your code inside Python using Pythonic conventions. And finally, Ray provides robust scheduling and resource management, including auto-scaling, including the scheduling of different tasks on different nodes. And it allows you to leverage both CPUs, GPUs, and multiple other hardware accelerators in your tasks. So in summary, Ray provides the compute strata, the infrastructure management, and solutions for the challenges of distributed computing. So how do we combine HuggingFace and Ray? We do that with the Ray AI Runtime's HuggingFace trainer. So we have, when designing the HuggingFace trainer, we have aimed for maximum simplicity and to provide a familiar interface that allows you to simply transfer your existing HuggingFace code and run it in a distributed fashion. So first of all, what we would do if we wanted to use the Ray AIR HuggingFace trainer is we would create a function into which we would simply put our existing HuggingFace code. So this could be, for example, what I've showcased previously. And the only difference is that instead of calling trainer.train at the end, we return the trainer object. Then we provide the Ray AIR scaling config, which determines how many workers we want to use and what sort of resources we want to assign to those workers. So in this example, we run the training on 3 workers, each with 1 GPU. And there are also other configuration objects that you may use that control different aspects of distributed training. Then we initialize the Ray AIR's HuggingFace trainer, passing in the function that we have created, the scaling config, as well as the data sets that we want to use. And finally, the only thing we need to do is to call the fit method on the HuggingFace trainer. So as you may notice, we have been slightly inspired by scikit-learn for Ray AIR because it provides a familiar and well-known interface. And it allows you to reuse the existing HuggingFace code without having to modify it in order to make it run in a distributed fashion. Finally, after the training is completed, The result object contains data such as metrics, the time it has taken for the training to complete, all of the checkpoints that have been saved, and more. So if we take a peek under the hood of the Ray AIR's HuggingFace trainer, what it does is it provides a way to conduct distributed data parallel or FSDP training on array cluster. And here we simply take advantage of the PyTorch DDP and FSDP implementations and the built-in support for those in HuggingFace. It allows us to run user-defined HuggingFace code without any changes. And we automatically convert the Ray datasets, about which I will talk a little bit more in later, to the format that is expected by HuggingFace. And it also provides built-in logging and monitoring with callbacks for different frameworks such as MLflow, weights and biases, and so on. So how does Ray train conduct the training? So the data set is sharded between multiple workers running on array cluster. Each of those workers gets a portion of the data set and conducts data parallel training, meaning that the gradients are communicated and synchronized after each iteration. If we want to change how many workers there are in our training run or what accelerators are being used, we can simply do that just by editing the scaling config. And this approach allows us to abstract away all of the underlying infrastructure, meaning we can focus on what's the most important. So Ray AIR as a whole uses Ray datasets as a common data format. And Ray datasets have several features that allow it to work in a distributed setting. So first of all, they provide various APIs to read from disk, cloud, or multiple other formats. Ray datasets are fully distributed, and they can be used on array cluster without any special considerations, and they can also handle data that is too big to fit in memory of one node or even on an entire cluster with thanks to the efficient usage of the Ray object store and objects spilling to disk. Ray AI Runtime also provides various out-of-the-box preprocessors for common machine learning tasks. And you can also write your own user-defined functions to map apply on Ray datasets in a parallel fashion. And the preprocessors are automatically applied during training in inference. So here in this example, we can use the HuggingFace tokenizer inside our user-defined function, and then we can use the Ray data batch mapper and pass it to the HuggingFace trainer, and then automatically the tokenization will be performed before the training and before inference later. So Ray AIR also provides multiple integrations for different logging and monitoring tools. There is built-in support for TensorBoard, MLflow, weights and biases, Comet ML, and more. And you can, of course, use the callback API that we provide to tailor it to your use case. And the result object provides a simple API to inspect the results of a training run after it has concluded. In order to ensure that the training run is robust, Ray AIR conducts automatic checkpointing during training, which you can, of course, configure to suit your needs. So, for example, you can only choose to keep the n best checkpoints according to some metric. And you can also choose to save the checkpoints to cloud, to disk, and other formats. You can resume the training from a checkpoint object, which is a unified API for storing models and other artifacts that have been created during training. And this automatic checkpointing and automatic resumption allows us to take advantage of cheaper spot instances. And Ray AIR will automatically resume training should a node be preempted. It will be automatically brought back up, and the checkpoint will be loaded and the training will be resumed. And furthermore, the checkpoint objects that are returned after training can be easily used for inference and serving with other parts of the Ray AIR ecosystem. So here is the typical Hugging Face training workflow as I have shown before. And now what we'll do is we'll see how we can easily change it into a distributed workflow with Ray AIR. So first, we just take the code that we have and we put it into a new function. And instead of calling trainer.train at the end, we simply return it. Then we initialize the Ray AIR Hugging Face trainer, passing our training function, the scaling config, and the datasets. So Ray datasets have an API to automatically convert a Hugging Face dataset into a Ray dataset. And then we just call trainer.fit. So to summarize, we are using Ray datasets for ingestion, which allows us to efficiently shard it across our Ray cluster. Then we can use our existing Hugging Face code. We can, for example, even take example code from the Hugging Face website, and it will also work out of the box. And it integrates with the rest of Ray AIR. So just to showcase some of those integrations, for example, we can use RayTune to conduct hyperparameter tuning. We simply pass the Hugging Face trainer into a Ray AIR tuner. We specify the search space and we call fit, and the tuner will conduct distributed training and tuning. We also provide ways to do scalable inference and serving with the returned checkpoint object obtained after the training. We can pass it to Hugging Face predictor for scalable parallel offline and online inference. And under the hood, the Hugging Face predictor uses Hugging Face pipelines, meaning that the output is the same as with non-distributed Hugging Face. But thanks to Ray dataset, it can be applied at scale and in parallel for both offline and online inference with Ray Serve. So here is how we would use the batch predictor from Ray AIR to do batch prediction using the checkpoint returned from Hugging Face. And we simply specify the Hugging Face predictor as the class that we are going to use, the task, the Hugging Face tokenizer, and all we have to do is call predict. So now I have a quick demo showing off a text classification workflow using Ray AIR and Hugging Face. Let me see if I can share it. Sorry. Not sure if this is sharing, unfortunately. Okay, there we go. So what I have here is I have a Jupyter notebook that is running on a Anyscale cluster. So Anyscale is our managed Ray service that we provide, but all of this can run with open source Ray without any problems. So let us just connect to the Ray cluster and quickly see what sort of resources we are working with. So this cluster has 16 GPUs contained in 4 nodes, each with 4 GPUs. And we will run our Hugging Face training using those GPUs and with 4 GPU workers per the training task. So this notebook is adapted from a non-distributed Hugging Face notebook where we simply do a fine-tuning of a model on a text classification task using the glue benchmark. For brevity, I will just quickly skip through the data loading part and the pre-processing part, but we are using the Hugging Face transformers tokenizer, and we are using Ray datasets to do the pre-processing at scale. I will also limit the size of the datasets so that we can finish the demo quicker. We define our pre-processing function, and this is the main part where we define the function that will be run on every worker using Ray. So we simply obtain the tokenizer and model from HuggingFace Hub. We define the training arguments, such as the learning rate, the batch size, and then we initialize the HuggingFace trainer and return it. And here we initialize the Ray AIR HuggingFace trainer. We pass the function that we have just defined, the scaling config, the data sets that we are going to use in Ray datasets format. The run config, which specifies that we'll use the MLflow as our logger, the checkpoint configuration, and the preprocessor, which will apply the tokenization. And all we have to do is simply call .fit. So there is some debug output, but what happens is that Ray will schedule tasks on our GPU nodes, and they will automatically start connecting, and we can already see that it detects that CUDA is available. And now all we need to do is simply just wait for training to finish. So we provide rich output for Jupyter notebooks. So this table is automatically updated as training progresses. And I have set it to run for 2 epochs. So we should see that the training is completed soon. And at the end, we'll obtain the result object. So we can see we obtain the metrics reported by HuggingFace, the checkpoint object, the directory where the results are saved, and so on. And now we can also perform hyperparameter tuning with Ray AIR. So let's say that we have several learning rates we want to consider for our fine tuning. We don't know which one minimizes the loss the best. So we can define a grid search over those 4 different learning rates. And RayTune provides...
Hey, sorry to interrupt. We need to wrap up. You have 2 minutes left.
That's right. That's right. Okay, so RayTune provides different advanced searching and scheduling algorithms, such as ASHA for early stopping. And finally, afterwards, we can do batch prediction using the batch predictor. So instead of using the tuned model, we'll use the one we have just trained. So all we have to do is pass the existing checkpoint, specify the HuggingFace predictor, and now batch prediction will automatically commence, and this is the result. So this is for a glue task, so we can see that the confidence score has been returned and whether the text contains offensive or non-offensive language. And that concludes the demo. Thank you so much.